Today, life on Earth is everywhere. Bacteria thriving in boiling hot springs, fish swimming in the deepest ocean trenches, plants growing in the harshest deserts. There are millions of species across every continent, filling every possible niche. Life has conquered this planet like nothing else in the known universe. From the Amazon rainforest with its impossible diversity, to the Arctic tundra where caribou migrate across frozen landscapes. From coral reefs that support thousands of species in a single ecosystem, to deep ocean vents where creatures exist without sunlight. Life is everywhere you look. We've catalogued over 8 million species, and scientists estimate there might be 100 million more we haven't discovered yet. Every environment on Earth, no matter how extreme, hosts some form of life. However, if you had looked at Earth 252 million years ago, the picture would have been apocalyptic. Not just difficult, apocalyptic. Over 96% of all marine species were dead. 70% of all land vertebrates had vanished. The planet's forests were gone, replaced by endless fields of fungi feeding on death. The oceans were purple and toxic, filled with hydrogen sulfide that would kill anything trying to breathe. Coral reefs that had thrived for millions of years were dissolved by acidic water. Entire ecosystems that had taken hundreds of millions of years to develop were wiped out in what amounts to a geological instant. If you're using this to fall asleep, that's literally why I make them. So subscribe, maybe, and tell me where you are and what time. I check comments and it's like Berlin at breakfast, Boston at bedtime, all at once. You know that feeling when you see footage of a natural disaster and think, how did anything survive that? Like watching a tsunami roll over entire cities, or seeing the aftermath of a massive earthquake. That overwhelming sense that the forces involved are so much bigger than anything life can handle. That's what happened to our entire planet 252 million years ago. Except it wasn't a few hours or days. It was tens of thousands of years of environmental hell that makes every disaster movie look like a children's cartoon. And here's the really crazy part. For over a century, nobody knew what caused it. See, scientists had been finding evidence of this mass extinction since the 1800s. They dig through rock layers from this period and find fossils, lots of them from before this time. The story of discovery starts with a Russian geologist named Vladimir Bochkarev in the 1960s. He's working in Siberia, mapping rock formations in one of the most remote regions on Earth. We're talking about wilderness so vast and empty that you can fly for hours without seeing a single sign of human habitation. Endless forests, frozen rivers, landscapes that look like they haven't changed since the Ice Age. Standard geological survey work for a Soviet research expedition. He's looking at layers of volcanic rock that stretch for hundreds of miles, trying to understand how they formed and when. Then he realizes he's not looking at ordinary volcanic deposits. He's standing on something that defies comprehension. A volcanic province so massive, it covers an area larger than Western Europe. Layer after layer of solidified lava stacked thousands of feet thick, extending far beyond the horizon in every direction. The sheer scale is mind-boggling. It's not just big, it's incomprehensibly enormous, like finding a mountain range made entirely of volcanic rock that stretches from London to Moscow. He calls them the Siberian Traps, using the geological term for step-like formations of igneous rock, and he knows he's looking at something catastrophic. But he has no idea he's found the weapon that nearly murdered an entire planet. For decades, geologists studied these formations with growing amazement and horror. They measured the volume, over 4 million cubic kilometers of lava. That's enough molten rock to bury the entire continental United States under 1,500 feet of basalt. To put that in perspective, Mount St. Helens, which disrupted weather patterns across North America when it erupted in 1980, produced about 1 cubic kilometer of material. To understand just how unprecedented this was, consider that the largest volcanic eruption in recorded history was Mount Tambora in Indonesia in 1815. It ejected so much ash and sulfur into the atmosphere that it caused global cooling for several years. Crops failed across Europe and North America. The year 1816 became known as the year without a summer. Hundreds of thousands of people died from famine and disease caused by climate disruption from this single eruption. The Siberian Traps produced the equivalent of a Mount Tambora eruption every few decades for 60,000 years. Let that sink in for a moment. 60,000 years of continuous volcanic devastation that makes the worst natural disaster in human history look like a minor inconvenience. What makes this discovery even more incredible is the timing. 252 million years ago puts us right at the end of the Permian period, a time when life on Earth had reached levels of diversity and complexity that wouldn't be seen again for tens of millions of years. The late Permian was a golden age for marine life. Coral reefs dominated the ocean floors, supporting incredibly complex ecosystems. On land, the first large herbivorous animals had evolved, creating food webs that supported diverse communities of predators and scavengers. This was before dinosaurs, before mammals, before flowering plants. But it was after life had figured out how to build complex multicellular organisms, how to create ecosystems with dozens of different species interacting in sophisticated ways. The Permian period represented the culmination of over 200 million years of evolutionary innovation since complex life had first emerged from the oceans. All of it was about to be tested by the worst environmental catastrophe in the history of the planet. What makes this discovery even more terrifying is the mechanism. This wasn't like a massive asteroid impact that kills everything instantly through shockwaves and debris clouds. The Permian extinction was slow torture for every living thing on Earth, a step-by-step dismantling of the entire biosphere that took place over thousands of years. Picture this. 252 million years ago, deep beneath what is now Siberia, something goes catastrophically wrong in the Earth's mantle. Maybe it's a massive mantle plume, a column of superheated rock rising from near the planet's core, carrying temperatures hot enough to melt steel. Maybe it's the destabilization of the entire regional geology, caused by the collision of tectonic plates. Maybe it's the breakdown of the boundary between the Earth's core and mantle, allowing superheated material to rush toward the surface. Scientists still debate the exact trigger, but they all agree on one thing. Whatever caused it was unprecedented in Earth's history. But the result was unambiguous. The crust above this instability began to crack and melt on a scale that defies imagination. Fractures thousands of miles long opened in the Earth's surface. Magma chambers the size of small countries began to form, and once it started, it couldn't stop. For the next 60,000 years, longer than modern humans have existed as a species, Siberia became a factory for producing environmental poison. Not just lava flows, though there were plenty of those. Imagine rivers of molten rock, hundreds of feet deep and miles wide, flowing across the landscape for months at a time. But the real killer wasn't the lava itself. It was what the lava was carrying. These eruptions were pumping massive quantities of toxic gases directly into the atmosphere. Carbon dioxide, sulfur compounds, chlorine, fluorine, mercury, everything that makes the atmosphere unbreathable and the oceans uninhabitable. We're talking about volcanic emissions on a scale that modern civilization has never seen and hopefully never will. The atmospheric chemistry went completely insane. Carbon dioxide levels spiked to over 2,000 parts per million, about 5 times higher than today's levels, which are already causing global warming. To put this in perspective, most climate scientists consider 450 parts per million of atmospheric CO2 to be extremely dangerous for modern civilization. The Permian atmosphere had over 4 times that concentration. Global temperatures rose by 10 to 15 degrees Celsius. Think about that for a moment. Current climate change has warmed the planet by about 1 degree Celsius, and that's already causing heat waves, droughts, and extreme weather events that kill thousands of people annually. The Permian warming was 10 to 15 times more severe. The poles, which had been temperate regions with forests and diverse animal communities, became subtropical zones where temperatures rarely dropped below 30 degrees Celsius, even in winter. The equator became a death zone where surface temperatures could exceed 60 degrees Celsius, hot enough to kill most large animals within hours of exposure. But the heat was just the beginning. The real killer was what happened to the oceans. See, when you pump that much carbon dioxide into the atmosphere, it doesn't just make the air hot. The oceans act as a massive carbon sink, absorbing about 30% of atmospheric CO2. When they do, the water becomes acidic through a chemical process that turns dissolved CO2 into carbonic acid. Ocean pH dropped by almost a full unit during the Permian extinction, turning seawater from its normal, slightly basic state into something approaching the acidity of battery acid. Anything with a calcium carbonate shell, coral reefs, shellfish, countless microscopic marine organisms that form the base of ocean food webs, began dissolving alive. Imagine every coral reef on Earth just melting away, every clamshell and snail shell turning to mush, every microscopic organism with a calcium skeleton simply dissolving into the water. The entire foundation of marine ecosystems disappeared in a matter of thousands of years. This is what scientists call ocean acidification, and it was happening at a rate about 100 times faster than the current acidification caused by human carbon emissions. Modern ocean acidification, which is already causing massive die-offs of coral reefs and shellfish, is a gentle tickle compared to what happened during the Permian extinction. Meanwhile, the warming oceans were losing their ability to hold oxygen. This is basic chemistry. Warm water holds less dissolved gas than cold water. You can demonstrate this with a warm soda that goes flat faster than a cold one. As ocean temperatures rose by 10 to 15 degrees, oxygen levels plummeted. Vast stretches of the ocean became anoxic, completely devoid of the oxygen that marine life needs to survive. In these oxygen-free waters, completely different chemistry takes over. Bacteria that thrive without oxygen begin producing hydrogen sulfide, the gas that smells like rotten eggs and is lethal to most life forms. These bacteria don't just produce a little hydrogen sulfide. When they dominate an ecosystem, they can generate concentrations high enough to poison the atmosphere above the water. The oceans literally began to poison themselves and then poison the air above them. Geological evidence shows that these hydrogen sulfide-producing bacteria were so successful that they turned entire ocean basins purple. That's the characteristic color of their photosynthetic processes, not the green of normal plants, but a deep purple that would have been visible from space. Imagine flying over Earth during this period and seeing purple seas stretching to the horizon, bubbling with toxic gas that kills anything that tries to breathe it. Any marine animal that tried to live in these waters would die from hydrogen sulfide poisoning within minutes. But there was nowhere else to go. The poisoned zones weren't limited to specific regions. They covered entire ocean basins. Marine life was trapped in a death trap that spanned the globe. On land, things were just as catastrophic. The extreme temperatures and atmospheric changes were killing plant life across entire continents. Forest fires became so common and widespread that charcoal deposits from this period can be found on every continent. But unlike normal forest fires that clear vegetation and allow new growth, these fires were followed by conditions so hostile that nothing could grow back. Without vegetation to hold soil in place, erosion accelerated to catastrophic levels. Rivers carried massive sediment loads into the dying oceans, further disrupting marine ecosystems that were already collapsing. The few remaining forests were replaced by landscapes dominated by fungi, organisms that thrive on decomposing organic matter. Basically, the planet's terrestrial ecosystems collapsed so completely that the dominant life form in many regions became the stuff that feeds on death. Imagine walking through what had once been a lush forest and finding nothing but endless fields of mushrooms and decomposing plant matter, with no living trees, no animals, no birdsong, just the silence of ecological collapse. But the Siberian traps weren't finished. The volcanic activity was interacting with the region's geology in ways that made everything exponentially worse. Much of Siberia sits on massive deposits of coal. Coal beds ignited when contacted by lava, creating underground fires that burned for thousands of years, pumping even more carbon dioxide into an atmosphere that was already saturated with greenhouse gases. These weren't small coal seam fires like the one that's been burning under Centralia, Pennsylvania for decades. These were continent-sized coal deposits, burning simultaneously, adding millions of tons of additional CO2 to the atmosphere every year. Salt deposits vaporized when heated, releasing chlorine and other halogen compounds that rose into the stratosphere and destroyed the ozone layer. Without ozone protection, deadly ultraviolet radiation reached Earth's surface at levels that could kill plants and animals, even if they had somehow survived everything else. The planet lost its natural sunscreen just when life was most vulnerable. Limestone decomposed under extreme heat, breaking down into lime and CO2, adding yet more carbon dioxide to an atmosphere already choking on greenhouse gases. Every geological process that could make things worse was happening simultaneously. It was a perfect storm of environmental catastrophes, each one making the others worse. Scientists call this positive feedback, not because it was positive for life, but because each effect amplified the others in an accelerating cycle of destruction. The warming atmosphere melted polar ice, reducing the planet's ability to reflect sunlight back to space, causing even more warming. The dying vegetation released stored carbon as it decomposed, adding to atmospheric CO2 levels. The acidifying oceans killed marine organisms that normally remove carbon from the water, reducing the ocean's capacity to absorb more atmospheric CO2. Ocean circulation patterns broke down, eliminating the currents that normally distribute heat around the planet and maintain stable climate zones. Every natural system that normally helps stabilize Earth's climate was either destroyed or turned into a source of additional instability. The planet was trapped in a death spiral that fed on itself, with each catastrophic change triggering new catastrophic changes in an endless cascade of environmental breakdown. And for most species, there was nowhere to run. This wasn't a regional disaster that animals could escape by migrating to safer areas. The atmospheric and oceanic changes were global. Toxic conditions reached every continent and every ocean basin. There were no climate refuges, no safe zones, no escape routes. The entire planet had become hostile to complex life. Scientists can see evidence of this planetary poisoning in rock formations around the world. Geological layers from this period contain unusually high concentrations of toxic metals, mercury, lead, nickel, chromium, that were vaporized by the volcanic activity and then settled out of the atmosphere everywhere on Earth. It's like forensic evidence from the greatest environmental crime in planetary history, preserved in stone for 252 million years. The extinction didn't happen all at once. It occurred in waves, each one eliminating different groups of organisms as conditions became progressively more intolerable. First, the most sensitive species died, those that couldn't tolerate rapid environmental changes, or those that depended on very specific ecological conditions. Marine organisms with calcium carbonate shells were among the first casualties, as ocean acidification dissolved their protective structures. Then, as food webs collapsed, predators and other specialized species followed. When the organisms at the base of food chains disappeared, everything that depended on them starved. Large predators, which needed huge territories and abundant prey, were particularly vulnerable. Complex ecosystem relationships that had taken millions of years to evolve were severed permanently. Finally, even the hardiest organisms succumbed to the poisoned environment. By the time it was over, the diversity of life on Earth had been reduced to levels not seen since the earliest days of complex multicellular organisms, over 300 million years earlier. Ecosystems that had taken hundreds of millions of years to develop were wiped out in what amounts to a geological instant. The marine extinction was particularly devastating. Before the Permian extinction, the oceans hosted incredibly diverse communities. Coral reefs covered vast areas of the seafloor, supporting thousands of species. Crinoids, sea lilies that looked like underwater flowers, formed forests on the ocean floor. Brachiopods, which resembled clams but were completely unrelated, filtered nutrients from the water in massive colonies. On land, the extinction was equally catastrophic but followed different patterns. The largest land animals were among the first to die. They required too much food and couldn't adapt quickly enough to rapidly changing plant communities. But surprisingly, many smaller animals died out too, especially those with high metabolic rates that made them vulnerable to toxins and temperature changes. The plant extinctions were particularly severe because they eliminated the foundation of all terrestrial ecosystems. When forests died and weren't replaced, all the animals that depended on them, herbivores, the predators that hunted herbivores, the scavengers that cleaned up after predators, the insects that pollinated flowers, the soil organisms that decomposed dead material, all of these complex relationships collapsed simultaneously. But here's what makes the Permian extinction even more terrifying from a modern perspective. For over a century, scientists thought this was just incredibly bad luck, a random volcanic catastrophe that happened once in Earth's history and would probably never happen again. It was treated as a fascinating but irrelevant piece of ancient history. Now we know that's not true. The chemical signature of the Permian extinction, the rapid increase in atmospheric CO2, the ocean acidification, the global warming, the breakdown of climate stability, looks disturbingly similar to what's happening today. The main difference is the rate. What took the Siberian traps 60,000 years to accomplish, human industrial activity is doing in about 200 years. We're running the same experiment on our planet's atmosphere and oceans, just much faster. And the results, so far, are following the same pattern. Dr. Lee Kump, a paleoclimatologist at Penn State who has spent decades studying the Permian extinction, puts it bluntly. The end Permian extinction is the closest thing we have to a perfect analogue for what we're doing to the planet now. The mechanisms are identical: rapid CO2 release, ocean acidification, global warming, That should terrify anyone who understands what happened 252 million years ago. Current atmospheric CO2 levels, which have risen from about 280 parts per million before the Industrial Revolution to over 420 parts per million today, are rising at a rate that's unprecedented in the geological record, except during mass extinction events. Ocean acidification is proceeding faster than it has in over 300 million years. Global temperatures are rising at speeds that most species can't adapt to quickly enough. We're not just risking a repeat of the worst environmental catastrophe in Earth's history. We're potentially creating something even worse by compressing the timeline from tens of thousands of years to a few centuries. But the story doesn't end with mass death. The most incredible part of the Permian extinction is what happened next, how life eventually recovered from the closest it has ever come to complete annihilation. For millions of years after the Great Dying, Earth remained largely barren. The few species that survived the extinction were living in a world with no established ecosystems, no stable food webs, no predictable environmental conditions. They had to rebuild the entire biosphere from scratch, starting with almost nothing. Recovery was agonizingly slow. In the marine realm, it took about 5 million years for biodiversity to return to even basic levels of complexity. Full recovery to pre-extinction diversity levels took over 10 million years, longer than the entire history of human evolution, and the life forms that eventually emerged were fundamentally different from what had existed before. The Permian extinction had functionally reset evolution. Entire groups of organisms that had dominated Earth for hundreds of millions of years were gone forever. The ecological niches they had occupied remained empty for millions of years, then were gradually filled by completely different types of organisms that evolved new ways of living. This is when many of the groups we're familiar with today first appeared. The early Triassic period, right after the extinction, saw the emergence of the first dinosaurs, the first mammals. In the oceans, entirely new ecosystems developed. The reef-building organisms that eventually replaced the extinct Permian corals were completely different species, using entirely different biological processes. Marine reptiles like ichthyosaurs and plesiosaurs evolved to fill ecological roles that had been occupied by completely different groups before the extinction. The oceanic food webs that supported these creatures had no direct evolutionary connection to what had existed before. Life didn't just recover, it diversified in entirely new directions, exploring evolutionary possibilities that had been closed off as long as the pre-extinction species dominated their ecological niches. The surviving species became the ancestors of virtually every major group of complex organisms alive today. Every mammal, every bird, every flowering plant, every modern fish, all of them trace their lineage back to the tiny fraction of species that made it through the environmental hell of the Permian extinction. We are all descendants of the survivors, all products of the greatest test life has ever faced. The genetic evidence for this bottleneck is written into the DNA of every complex organism on Earth. When biologists construct evolutionary trees showing how different species are related to each other, there's a massive constriction right around 252 million years ago. Evidence that almost everything alive today evolved from a very small number of ancestral species that survived the Great Dying. Your house cat carries genes from creatures that lived through hydrogen sulfide oceans and 60-degree temperatures. The trees in your backyard descend from plants that survived in landscapes dominated by fungi feeding on death. The birds outside your window evolved from lineages that made it through the worst environmental catastrophe in planetary history. Every time you see a complex, living organism, from insects to elephants, from roses to redwood trees, you're looking at a descendant of something that was tough enough to survive conditions that killed 96% of everything else. But what exactly allowed some species to survive when so many others died? Scientists have spent decades trying to understand the factors that determined who lived and who died during the Permian extinction. and they've identified several key survival traits. Size mattered, but not the way you might expect. Many of the largest animals died out early. They required too much food and were too specialized to adapt quickly to rapidly changing conditions. A massive predator that needed to eat hundreds of pounds of meat every day couldn't survive when prey populations crashed. But the smallest animals often died too, especially those with high metabolic rates that made them vulnerable to toxins and temperature changes. The survivors were often medium-sized generalists, organisms that could eat a variety of foods, tolerate a wide range of environmental conditions, and didn't require highly specialized habitats to survive. Animals that could switch from eating plants to eating insects to scavenging dead material when necessary. Plants that could grow in different soil types and adjust their metabolism to changing atmospheric chemistry. Geographic location was crucial for survival. Species living near the equator, where temperatures became most extreme during the global warming phase, had much lower survival rates than those in higher latitudes where conditions remained relatively more tolerable. Organisms living in shallow marine environments, where ocean acidification was most severe and hydrogen sulfide concentrations were highest, were much more likely to go extinct than those in deeper waters, where conditions were somewhat buffered. Some of the highest survival rates were found among species living in freshwater environments, lakes and rivers that were somewhat isolated from the worst oceanic changes. These freshwater systems still suffered from global warming and atmospheric toxins, but they avoided the direct effects of ocean acidification and hydrogen sulfide poisoning that devastated marine ecosystems. Metabolic flexibility was perhaps the most important factor determining survival. Organisms that could dramatically slow down their metabolism during bad times, switch between different food sources when their preferred nutrition became unavailable, or enter dormant states when conditions became temporarily intolerable, were much more likely to make it through the crisis. This is why many of the survivors were relatively simple organisms: bacteria, fungi, small arthropods, hardy plants with flexible reproductive strategies. They might not have been the most impressive or complex creatures on the planet, but they were adaptable in ways that highly specialized organisms were not. Reproductive strategy also played a crucial role in survival. Species that reproduced quickly and had short generation times could evolve rapidly in response to changing environmental conditions. Animals and plants that could produce many offspring and had multiple generations per year, but perhaps the most important survival trait was something that's very difficult to measure from the fossil record: behavioral flexibility. The species that made it through the Permian extinction were probably those that could dramatically modify their behavior when their normal survival strategies stopped working. Animals that could find completely new food sources when their preferred prey went extinct. Plants that could adjust their growing patterns, flowering times, and root structures when soil chemistry and climate patterns changed. Organisms that could migrate to entirely new types of habitats when their original homes became uninhabitable. Marine organisms that normally lived in shallow water but could survive in deeper zones. Land animals that could switch between different types of vegetation or even between plant and animal food sources. Species that could tolerate much higher or lower temperatures than they normally preferred. The survivors weren't necessarily the strongest, the smartest, or the most numerous before the extinction began. They were the most adaptable, the ones that could change their entire way of life when the world around them became unrecognizable. This has profound implications for understanding how life might respond to current environmental changes. The species most likely to survive rapid climate change and ecosystem disruption aren't necessarily the ones we think of as most advanced or ecologically important. They're the ones that can adjust to new conditions quickly and dramatically. Cockroaches, rats, pigeons, dandelions. Organisms that many people consider pests or weeds are actually masters of evolutionary survival. They're dietary generalists that can eat almost anything, habitat generalists that can live almost anywhere, and behavioral generalists that can adjust their activity patterns, social structures, and reproductive strategies when conditions change. Meanwhile, highly specialized species, polar bears that depend on Arctic sea ice, coral reefs that require very specific water chemistry and temperature ranges, forest species that can't survive habitat fragmentation, migratory animals that depend on predictable seasonal patterns. The fossil record suggests that recovery from mass extinctions follows certain predictable patterns. First, immediately after the extinction event, opportunistic species rapidly multiply to fill the empty ecological niches left by extinct species. These disaster taxa are usually small, fast-reproducing organisms that can take advantage of the lack of competition and the abundant resources left behind by ecosystem collapse. During the early Triassic period, right after the Permian extinction, many ecosystems were dominated by a few species of small, generalist animals and hardy plants that could survive in the harsh post-extinction environment. These weren't necessarily the most impressive organisms, just the ones that could hang on while the planet slowly healed. Then, over millions of years, some of these disaster survivors gradually evolved into new forms that became increasingly specialized for particular environments or lifestyles. As conditions stabilized and resources became more predictable, natural selection began favoring organisms that could efficiently exploit specific ecological niches. Eventually, complex ecosystems redeveloped, often with entirely new groups of organisms filling ecological roles that had previously been occupied by completely different species. The end result was a biosphere that was often more diverse and complex than what had existed before the extinction, but built from completely different evolutionary building blocks. This process of evolutionary radiation, the rapid diversification of surviving species into many new forms, has happened after every major extinction event in Earth's history. The recovery from the Permian extinction was just the most dramatic example because the extinction itself was so severe. But recovery is never guaranteed for individual planets. There are examples in our own solar system of worlds that experienced runaway environmental changes and never recovered. Venus, for instance, has atmospheric conditions that are probably similar to what Earth experienced during the worst phases of the Permian extinction. Extreme temperatures, atmospheric pressures dozens of times higher than Earth's, clouds of sulfuric acid, surface conditions that would melt lead. The difference is that Venus never developed the complex biological and geological feedback systems that eventually removed excess CO2 from Earth's atmosphere and allowed global temperatures to stabilize. Earth's recovery from the Permian extinction depended not just on the resilience of life, but on the interaction between living organisms and geological processes. Life itself played a crucial role in planetary healing. Plants that evolved after the extinction began pulling massive amounts of CO2 out of the atmosphere through photosynthesis, gradually reducing the greenhouse effect. Marine organisms that survived the oceanic catastrophe eventually re-established populations large enough to remove carbon from seawater and deposit it as limestone and other carbonate minerals on the ocean floor. Soil bacteria developed new biogeochemical cycles that helped restore normal atmospheric composition. Weathering of volcanic rocks, accelerated by the interaction with plant roots and microbial communities, helped neutralize acidic conditions and stabilize climate patterns. In other words, life didn't just passively survive the Permian extinction, it actively participated in healing the planet, creating the conditions that allowed for long-term recovery and the eventual explosion of biodiversity that followed. This gives us some reason for hope regarding current environmental challenges, but it also comes with a sobering timeline. Even if life on Earth can eventually recover from whatever damage we're currently doing to the atmosphere and oceans, that recovery process will take millions of years, far longer than human civilization has existed, and certainly much longer than would be useful for preserving current ecosystems and species. The Permian extinction teaches us that planets can survive almost anything given enough time, but individual species and ecosystems are far more fragile than the biosphere as a whole. The specific communities of organisms that exist today, including the ecosystems that support human civilization, could disappear forever, even if life itself continues in some form. Modern coral reefs, tropical rainforests, polar ecosystems, temperate forests, All of these could vanish completely, to be replaced millions of years later by entirely different biological communities that we wouldn't recognize. The recovery of biological diversity doesn't mean the recovery of any specific forms of life that we care about preserving. But there's another lesson from the Great Dying that's even more directly relevant to our current environmental situation. Each individual change, the initial warming, the ocean acidification, the breakdown of atmospheric circulation patterns, the release of hydrogen sulfide, might not have been enough to cause a mass extinction on its own. But together, they created a cascade of environmental failures that overwhelmed the adaptive capacity of most life forms. This is exactly what concerns scientists about current environmental changes. We're not just dealing with climate change, or just ocean acidification, or just habitat destruction, or just pollution, or just invasive species. We're dealing with all of these problems simultaneously, and they're all making each other worse in ways that are difficult to predict. Climate change is accelerating habitat destruction by shifting temperature and rainfall patterns faster than ecosystems can adapt. Habitat destruction is reducing the resilience of ecosystems to climate change by fragmenting populations and eliminating the genetic diversity that allows species to adapt to new conditions. Ocean acidification is weakening marine food webs just when they're already stressed by warming temperatures and pollution. Invasive species are spreading more rapidly because native ecosystems are weakened by multiple other stresses. We're creating the same kind of cascading environmental failure that killed 96% of marine species 252 million years ago. The main difference is that this time, one species, us, is causing all the changes instead of geological processes. Dr. Peter Ward, a paleontologist at the University of Washington, who has spent decades studying mass extinctions, argues that we're already well into the early stages of Earth's sixth great extinction event. The pattern is identical to what we see in the fossil record from previous mass extinctions, he says. Rapid environmental change, ecosystem collapse, cascading species losses. The only difference is the speed, and that actually makes our situation more dangerous, not less. Species that might be able to adapt to gradual environmental changes over thousands of years simply can't adjust quickly enough when the same changes happen in decades or centuries. But unlike the Siberian traps, which erupted for 60,000 years regardless of their environmental impact, humans have the theoretical ability to recognize what we're doing and change course. We can study the Permian extinction, understand the mechanisms that drive mass extinction events, and potentially alter our behavior to avoid triggering the same cascading failures. The question is whether we will, and whether we'll do it quickly enough to prevent irreversible changes to the biosphere. The Permian extinction shows us both the incredible fragility and the amazing resilience of life on Earth. It demonstrates that even the worst environmental catastrophe in planetary history isn't necessarily the end of everything. Life has an almost supernatural ability to survive, adapt, and eventually flourish again, even after losing 96% of its diversity. But it also shows us that recovery takes geological timescales measured in millions of years, and that the specific forms of life that exist at any given time, including us, can vanish forever if environmental changes happen too quickly for adaptation to keep up. Every species alive today carries the genetic legacy of the Permian survivors, the molecular signatures of organisms that refused to give up when the planet itself seemed to be dying. We are all products of the greatest test life has ever faced. The survivors of the Great Dying didn't make it through because they were lucky. They survived because they were tough enough, adaptable enough, and flexible enough to keep going when conditions became almost uninhabitable. Those traits are still written into the DNA of every complex organism on Earth. The capacity for metabolic flexibility that allowed ancient organisms to survive in poisoned environments. The behavioral adaptability that let them switch to entirely new survival strategies when their old approaches stopped working. The reproductive resilience that allowed tiny populations to rebuild entire ecosystems from almost nothing. But survival traits alone weren't enough. The Permian recovery also required something else. Time. Massive amounts of time for natural processes to restore atmospheric balance, for ocean chemistry to stabilize, for soil systems to redevelop, for climate patterns to settle into predictable cycles. The early survivors lived in a world that was still hostile, but gradually becoming more habitable. For the first few million years after the extinction, Earth was dominated by what paleontologists call disaster taxa, opportunistic organisms that could thrive in the simplified, resource-rich environment left behind by ecosystem collapse. These weren't the most impressive creatures. Many of them were small, generalist organisms that looked almost primitive compared to the complex, specialized species that had dominated pre-extinction ecosystems. But they had one crucial advantage. They could survive and reproduce in conditions that would kill more sophisticated organisms. Over millions of years, these disaster survivors gradually evolved into more complex forms. Natural selection began favoring organisms that could efficiently exploit specific resources as competition increased and ecological niches became more defined. The simple, generalist survivors became the ancestors of increasingly specialized descendants. By the Middle Triassic period, about 15 million years after the extinction, Earth was starting to look alive again. New types of coral reefs were forming in the oceans, built by organisms completely different from the extinct Permian corals. On land, the first dinosaurs were beginning to diversify into the ecological roles that would make them the dominant vertebrates for the next 150 million years. But it took much longer for true biodiversity to return. Full recovery to pre-extinction levels of species diversity required over 30 million years, about 6 times longer than the period from the extinction of dinosaurs to the present day. The Permian extinction had cut so deeply into the tree of life that evolution needed an enormous amount of time to rebuild the same levels of complexity. And when that complexity finally returned, it was built on entirely different foundations. The dominant organisms of the post-Permian world, dinosaurs, mammals, flowering plants, modern insects, had no direct evolutionary connection to the groups that had ruled before the extinction. The Great Dying had essentially cleared the evolutionary slate and allowed completely new experiments in complex life. This pattern of destruction and renewal has happened multiple times in Earth's history, but never as severely as during the Permian extinction. Each mass extinction event creates opportunities for new groups of organisms to evolve and fill the ecological roles left empty by extinction. But the scale of the Permian catastrophe was so vast that it fundamentally reset the trajectory of evolution on Earth. Without the Permian extinction, dinosaurs might never have evolved. Mammals might have remained small, nocturnal creatures indefinitely. The flowering plants that now dominate terrestrial ecosystems might never have developed their sophisticated relations. All of it was lost forever when the Siberian traps began their 60,000-year assault on the biosphere. The question that haunts scientists studying the Permian extinction is whether we're witnessing the beginning of a similar catastrophe today. The parallels are undeniable. Rapid release of greenhouse gases into the atmosphere, ocean acidification proceeding at rates not seen since the Great Dying, global temperatures rising faster than most species can adapt, ecosystems collapsing in cascading failures as multiple stresses interact and amplify each other. Dr. Jonathan Payne, a paleobiologist at Stanford University who studies extinction and recovery patterns, has spent years comparing the Permian catastrophe to current environmental changes. His research suggests we're not just facing another mass extinction, we're potentially facing something worse. The Permian extinction was caused by geological processes that operated over thousands of years, he explains. What we're doing to the planet is similar in scale, but happening in decades instead of millennia. Evolution simply can't keep up with that pace of change. Modern species are facing environmental stresses that are similar to what killed 96% of life 252 million years ago, but compressed into timeframes that make adaptation almost impossible. Climate zones are shifting faster than trees can migrate. Ocean chemistry is changing faster than marine organisms can evolve new physiological tolerances. Habitat destruction is fragmenting ecosystems faster than populations can establish new migration routes or breeding patterns. The result is what biologists call an extinction debt, species that are already doomed by current environmental changes but haven't died yet because it takes time for populations to collapse completely. Many scientists believe we're witnessing the early stages of a mass extinction that will eventually rival the Great Dying in scope, even if its immediate effects seem less dramatic. But there's one crucial difference between the Permian extinction and what's happening today. The Permian extinction offers both a warning and a strange form of hope. The warning is clear. Planets can experience environmental catastrophes so severe that they eliminate almost all complex life. There's nothing inevitable about the continued existence of diverse ecosystems or stable climate patterns. The natural world that supports human civilization is more fragile than most people imagine, and we're currently conducting an uncontrolled experiment with the same atmospheric and oceanic systems that regulate habitability. But the hope is equally real. Life on Earth survived the worst environmental catastrophe in planetary history, not just survived, eventually flourished beyond anything that had existed before. The biosphere showed an almost supernatural capacity to heal from catastrophic damage and create new forms of complexity and beauty from the ashes of ecological collapse. That same resilience exists today. Evolution hasn't stopped working. Natural selection is still operating. Organisms are still adapting to environmental changes, sometimes in ways that surprise scientists. Some species are already showing genetic and behavioral adaptations to higher temperatures, more acidic oceans, and altered precipitation patterns. But resilience has limits, and recovery takes time that we may not have. The Permian survivors had millions of years to rebuild ecosystems without any additional environmental pressure. Current species are trying to adapt to climate change while simultaneously dealing with habitat destruction, pollution, invasive species, and a dozen other human-caused stresses. We're asking life on Earth to perform the same recovery miracle that followed the Great Dying, but while we continue to make conditions worse instead of better. The researchers who discovered the connection between the Siberian traps and the Permian extinction, scientists like Paul Wignall, Michael Benton, and dozens of their colleagues, have given us more than just an amazing scientific discovery. They've provided a mirror that shows us exactly what we're doing to our own planet. When we look at the geological evidence of those 60,000 years of volcanic devastation, we're not just learning about ancient history. We're looking at the most comprehensive example we have of what happens when atmospheric chemistry goes haywire and ecosystems collapse under environmental stress. The Siberian traps show us that planets can experience catastrophic environmental changes that eliminate most complex life. But the recovery that followed shows us that life has an almost infinite capacity to adapt, survive, and create new forms of complexity when given enough time and stability. We are the species that discovered this history, the species that can read the geological record and understand what it means, the species that can look at atmospheric CO2 measurements and recognize that we're conducting the same experiment that killed 96% of marine life 252 million years ago. We're also the species that could choose to do something different. The Permian extinction is both a warning and a promise. A warning that environmental catastrophes can happen, that they can be far worse than anything in human experience, and that they can eliminate forms of life that took hundreds of millions of years to evolve. But also a promise that life is tougher than almost anything the planet can throw at it, that survivors can rebuild entire biospheres from almost nothing, and that the capacity for resilience and adaptation runs deeper than we often realize. 252 million years ago, the Siberian traps erupted for 60,000 years and nearly sterilized the planet. Ocean temperatures rose by 15 degrees, Atmospheric CO2 reached levels 5 times higher than today. The oceans turned acidic and purple, filled with hydrogen sulfide that poisoned the air above them. Forests disappeared and were replaced by fungi feeding on death. 96% of marine species died. 70% of land vertebrates vanished. Life came closer to complete extinction than it ever has before or since. But life didn't give up. The survivors, tough, adaptable, flexible organisms that could change their entire way of life when the world became unrecognizable, kept going. They evolved new survival strategies, developed new ecological relationships, and gradually rebuilt the biosphere from almost nothing. Today, there are millions of species living on Earth. We've developed technologies that let us understand the deep history of our planet, predict the consequences of environmental changes, and potentially alter our impact on global systems. We are the descendants of the Permian survivors, and we carry their capacity for adaptation and resilience. The Siberian traps couldn't choose to stop erupting. We can choose to stop the modern equivalent of volcanic emissions. The Permian survivors couldn't understand what was happening to their world or plan for recovery. We can do both. Whether we will, and whether we'll do it soon enough, remains the most important question facing our species and our planet. The answer will determine whether the next chapter in Earth's history is another great dying, or the first time in planetary history that a species chose to prevent one. But to understand just how remarkable the Permian recovery really was, we need to dig deeper into what those first few million years after the extinction actually looked like. Because the picture that emerges from the geological record is both more horrifying and more inspiring than most people realize. The immediate aftermath of the Great Dying wasn't just a world with fewer species. It was a world where the basic rules of ecology had completely broken down. Food webs that had been stable for millions of years simply didn't exist anymore. Nutrient cycles that had regulated soil chemistry and ocean productivity for geological ages had collapsed. Even the relationship between predators and prey had been reset to almost nothing. Imagine trying to understand an ecosystem where there are only a handful of species left, scattered across continents and ocean basins, with no established relationships between them. It's like trying to rebuild a complex machine when 96% of the parts are missing, and you've lost the instruction manual. The fossil record from the early Triassic period shows us exactly what this looked like. In the oceans, vast areas of the sea floor were covered by just a few species of small bivalves and gastropods, the marine equivalent of weeds growing in the ruins of a bombed city. These weren't sophisticated ecosystems. They were biological emergency shelters, simple communities of hardy organisms trying to survive in a world that was still actively hostile to complex life. On land, the situation was even more stark. Huge areas that had once supported diverse forests and complex animal communities were dominated by a single genus of seed fern called Pluramea. These weren't impressive plants. They looked like oversized bottle brushes, grew in dense monocultures, and had extremely simple root systems. But they could tolerate the extreme temperatures, unstable soil chemistry, and toxic atmospheric conditions that killed everything else. For millions of years after the extinction, vast stretches of the continents looked like alien landscapes. Endless fields of identical plants growing under a sky with atmospheric chemistry unlike anything in Earth's previous history. No flowers, no complex trees, no understory vegetation, no large herbivores, no predator-prey relationships, just Pluramea forests stretching to the horizon, supporting tiny populations of small, generalist animals that could survive on whatever resources these simplified ecosystems provided. But even in this devastated world, evolution was working. Natural selection doesn't stop during mass extinctions. It just operates under completely different rules. Instead of favoring specialization and efficiency, it favors flexibility and tolerance. Instead of rewarding organisms that can exploit specific ecological niches, it rewards those that can survive in unstable, unpredictable environments. The organisms that lived through the early Triassic were essentially beta-testing new approaches to survival. Some experiments failed. Lineages that couldn't adapt to the slowly changing conditions went extinct, but others succeeded in ways that would shape the entire future of life on Earth. Take the archosaurs, for example. These were reptiles that had been minor players in Permian ecosystems, overshadowed by more successful groups that dominated most ecological niches. But archosaurs had one crucial advantage during the recovery period. They were exceptionally good at regulating their body temperature and metabolism. In the extreme, unstable climate of the early Triassic, this metabolic flexibility was the difference between life and death. While other reptiles were limited to narrow temperature ranges or specific types of habitats, archosaurs could survive temperature swings of 20 to 30 degrees Celsius and adjust their activity levels to match available resources. Over millions of years, this physiological advantage allowed archosaurs to diversify into ecological roles that had been left vacant by extinction. Some became large predators, filling the niche left by extinct mammal-like reptiles. Others became herbivores, taking advantage of the slowly recovering plant communities. Still others became small, agile hunters that could exploit the growing populations of early mammals and other small vertebrates. By the Middle Triassic, archosaurs had become the dominant land vertebrates on Earth. Their descendants would include crocodiles, pterosaurs, and dinosaurs, groups that would rule terrestrial ecosystems for the next 200 million years, all because their ancestors had been flexible enough to survive the ecological chaos that followed the Great Dying. The same pattern played out in the oceans, where groups that had been evolutionary also-rans before the extinction suddenly found themselves with unlimited opportunities. Modern sharks, for instance, trace their lineage back to cartilaginous fish that survived the Permian extinction, when most other marine predators died out. Before the Great Dying, sharks were just one of many types of marine predators, competing with placoderms, early bony fish, and various marine reptiles for food and territory. But their flexible body plan, efficient metabolism, and broad dietary tolerance made them perfect survivors in the simplified ecosystems of the early Triassic. As marine ecosystems slowly recovered, sharks diversified explosively. Some became massive filter feeders, taking advantage of the gradually recovering plankton populations. Others became fast pursuit predators, exploiting the new communities of bony fish that were evolving to fill empty ecological niches. Still others became bottom dwellers, feeding on the invertebrate communities that were slowly recolonizing the seafloor. The evolutionary radiation of sharks during the Triassic recovery period established patterns that persist today. Modern shark diversity, from whale sharks to hammerheads to great whites, can be traced back to the survival and diversification of a few lineages that made it through the Permian extinction, when most other marine predators went extinct. But perhaps the most important evolutionary development during the recovery period was something that would seem almost insignificant at the time: the emergence of new plant communities that could form the foundation for complex terrestrial ecosystems. The Pluramea monocultures that dominated the early Triassic landscape were ecological dead ends. They could survive in post-extinction conditions, but they couldn't support the kind of complex animal communities that had existed before the Great Dying. They didn't produce diverse food sources, didn't create complex habitat structures, and didn't establish the kind of soil relationships that allow ecosystems to become self-sustaining. But gradually, over millions of years, new types of plants began to evolve from the survivors of the extinction. Conifers that could form real forests instead of simple monocultures. Seed plants that could create complex relationships with soil, fungi, and bacteria. early flowering plants that would eventually revolutionize terrestrial ecosystems by developing sophisticated relationships with insect pollinators. These weren't just new species, they were new approaches to being a plant. The pre-extinction flora had been dominated by groups that had evolved hundreds of millions of years earlier and had become locked into relatively simple ecological strategies. The post-extinction flora was free to experiment with completely new ways of capturing sunlight, processing nutrients, reproducing, and interacting with animal communities. The conifers that emerged during the Triassic recovery period, for instance, developed needle-like leaves that were much more efficient at conserving water and nutrients than the broadleaves of most pre-extinction plants. This allowed them to survive in the still harsh climate of the recovery period, while also supporting more complex animal communities than the simple Pluramea forests. More importantly, these new conifers could form the kind of stable, long-lived forest ecosystems that create predictable habitat structures over centuries or millennia. Animals could evolve to specialize in living in conifer forests, feeding on conifer seeds, nesting in conifer branches, and using conifer trunks for shelter and territory. This stability was crucial for the recovery of complex ecosystems. Specialization, the evolution of organisms that are perfectly adapted to specific ecological roles, only works when those ecological roles remain consistent over many generations. The early post-extinction world had been too unstable and unpredictable to support specialization. But as plant communities became more stable and predictable, animals could begin evolving the kind of sophisticated ecological relationships that make ecosystems resilient and self-sustaining. By the late Triassic period, about 30 million years after the extinction, Earth was finally starting to look like a living planet again. Conifer forests covered vast areas of the continents, supporting diverse communities of herbivorous and carnivorous reptiles. Marine ecosystems had developed complex food webs with multiple levels of predators and prey. Coral reefs, built by entirely new groups of organisms, were beginning to form the foundation for diverse marine communities. But the most remarkable development was the emergence of the groups that would dominate Earth for the next phase of its history. The first dinosaurs appeared during the late Triassic, emerging from archosaur ancestors that had survived the extinction and gradually diversified during the recovery period. The first mammals evolved from therapsid survivors that had spent millions of years as small, generalist omnivores in the simplified post-extinction ecosystems. Even more importantly, the recovery period had established entirely new ecological principles that would govern how ecosystems functioned for the rest of Earth's history. The pre-extinction world had been dominated by organisms that had evolved during relatively stable climate periods and had become highly specialized for specific environmental conditions. When those conditions changed rapidly during the extinction, specialization became a death sentence. The post-extinction world was built by organisms that had been selected for flexibility, adaptability, and tolerance of environmental change. This created ecosystems that were inherently more resilient to future environmental disruptions. Communities of organisms that could adjust their behavior, metabolism, and ecological relationships when conditions changed. This resilience would be tested repeatedly over the following 250 million years. The Triassic-Jurassic extinction, 200 million years ago, eliminated many species, but didn't cause the kind of ecosystem collapse that followed the Permian event. The asteroid impact that ended the age of dinosaurs 66 million years ago was devastating, but allowed for relatively rapid recovery by mammalian survivors. None of these later extinctions approached the severity of the Great Dying because none of them had to deal with ecosystems that were fundamentally unstable. The Permian extinction had created evolutionary pressure for resilience and adaptability that made all subsequent life more capable of surviving environmental challenges. In a very real sense, every complex ecosystem that has existed since the Triassic period has been a product of the survival strategies developed during the Permian recovery. The mammals that eventually replaced dinosaurs as dominant land vertebrates were descendants of tiny generalists that had learned to survive anything during the post-extinction chaos. The flowering plants that now dominate most terrestrial ecosystems evolved from lineages that had been selected for flexibility and rapid adaptation during the recovery period. Even humans carry the evolutionary legacy of the Great Dying. Our mammalian ancestors survived the Permian extinction as small, adaptable organisms that could adjust their diet, behavior, and habitat requirements when environmental conditions changed. The intelligence, social cooperation, and behavioral flexibility that characterize modern humans can be traced back to survival strategies that were refined during the most challenging period in the history of complex life. We are not just descendants of the Permian survivors, we are products of the evolutionary lessons learned during the recovery that followed. Our capacity for innovation, cooperation, and adaptation to new environments reflects genetic and behavioral patterns that were established during the 30 million years it took for life to rebuild itself after nearly going extinct. This gives us a unique perspective on current environmental challenges. We are the first species in Earth's history that can study mass extinction events, understand the recovery process, and potentially apply those lessons to prevent or minimize future ecological catastrophes. The Permian extinction and recovery teach us that life is both more fragile and more resilient than we often realize. Ecosystems that seem stable and permanent can collapse completely when environmental conditions change too rapidly. But life also has an almost unlimited capacity to adapt, evolve, and create new forms of complexity when given sufficient time and stability. The question facing us now is whether we can provide that time and stability for ourselves and for the other species sharing our planet. The environmental changes we're currently causing are similar in many ways to what triggered the Great Dying 252 million years ago. But unlike the geological processes that caused the Permian extinction, we have the ability to recognize the danger and potentially change course. Whether we will make that choice, and whether we'll make it soon enough, may determine not just the future of human civilization, but the entire trajectory of evolution on Earth for millions of years to come.